So welcome everyone at the next session. In this session, we'll talk about acceleration analysis. We have talked about velocity and point position analysis. Now, it also should be clear to you that acceleration is the change of velocity over time. Now, velocity itself, we have seen, is a vector. And this vector, for example, if we have a point at the time t, this point was this position, and we have a path that this point is moving along, and the time, let's say t plus delta t, which is here now, it's pp prime. Then it has a new velocity vector, linear velocity vector, which is vp prime. Now we have said also that linear velocity is always perpendicular to the radius of rotation. So basically this is the radius of rotation in these two positions. It's clear that the linear velocity has changed over time. The change of velocity over time is the acceleration, and it's also vector quantity, which is basically, this is vp, let's say, this is v prime, and the closing vector is the delta vp, which representing the change over time. Now, if delta t goes to 0 as a limit, so basically we will end up with the first derivative of velocity vector over time, which represent the linear acceleration. And here basically this, which is actually also the second derivative of the position vector over time. So it is a vector, which means it has a magnitude and a direction. Now, as velocity, we have actually linear acceleration and angular acceleration. Now, the linear acceleration represents the change of the linear velocity over time. Now, the linear velocity is a vector, and it may change in two different ways. So vector might change in two different ways. The first way, actually, it changes its magnitude. So the linear velocity might change in magnitude first, and the change of the magnitude is represented by the first actually component you would consider of acceleration, which is called the tangential acceleration. So the tangential acceleration represents the change of the magnitude of the linear velocity over time. And it is a vector, of course. It actually lies along the same vector, or the same vector as the linear velocity, which is here, which is always perpendicular to the radius of movement. And yeah, this is basically the tangential acceleration. Now, it doesn't, if it lies on the same vector as linear velocity, that doesn't mean it has always the same direction as the velocity, of course. If it is in the same direction, that means there's acceleration. And if it is actually in the opposite direction, that means there's braking or the acceleration of the velocity. Okay. Now, the other actually way the linear velocity may change is its orientation. So, let's say if I am moving along this path, which is a curvy path, then of course this velocity would change its orientation. So it's not always in this direction. Next point will be like this, then like this, then like this, and so on. Now, that change over time is represented by another acceleration component, which is called the normal acceleration. Now, the normal acceleration lies along the radius of movement. So basically it is this one. That means it's always perpendicular to both the linear velocity and the tangential acceleration. Okay, so it's actually representing the change of path. If I am moving on a curvy movement, if I am moving on straight line, that means there's no tangential acceleration because the radius is infinite, and basically there's no tangential acceleration. There's no normal acceleration, but we have only tangential acceleration that is representing either we are speeding up, as I said, or accelerating or decelerating. Now, the common unit is basically of acceleration is feet per square second, or inch per square second, for example, or meter per square second. Now, the second type of acceleration, which is the angular acceleration, that clearly represents the change of the angular velocity over time. Okay, so we have seen that we have linear velocity and we have angular velocity. Here again we have also linear acceleration, we have angular acceleration, and the angular acceleration represents the change of the angular velocity over time. And the direction of the angular acceleration is the direction of motion when the angular velocity increases or the link accelerates. So if we have, let's say, a rotating link, and this link starts to accelerate its movement, accelerate its rotation, in this case, the angular acceleration would be in the same direction as the angular velocity. If this basically the opposite direction, that means that we have deceleration in the angular velocity. Okay, so this basically the difference. Like angular velocity for a link, all points on a link, they have the same angular acceleration, and also they have the same angular velocity, but they have different linear velocity, and they have different linear acceleration. All right. So now we talked about the two components of acceleration, and here we actually come to these two components, and basically we have the tangential acceleration and linear acceleration. They are calculated or estimated in two different ways. Let's start with the tangential acceleration, which as I said, actually it has the same axis or same vector or the same orientation as the linear velocity, okay, and is actually expressed by, let's say, it is a change of the magnitude, right, over time. And the magnitude of velocity we have seen is, or linear velocity, is expressed by the multiplication of the angular velocity with the radius of movement. And this would, for example, if we just solve this problem, we would get up with the, or get into with the formula for the tangential acceleration, which is basically the radius multiplied by the angular acceleration. So the linear velocity is equal to the angular velocity multiplied by the radius, and the tangential acceleration is equal to the radius multiplied by the angular acceleration. Okay, so it's always, when it comes to this formula, like the linear velocity, it's important to express the acceleration, for example, the angular acceleration as radians per squared second or per squared time. Now the second basically component, which is the normal acceleration, which represent, as I said, the change of direction, orientation over time, which creates a normal acceleration. And this basically, this we have the same point that is moving over time. This is the first orientation, and this is the second orientation over time. And because of the change of that orientation, we got the normal acceleration. All right, so to derive basically the formula of the normal acceleration is a bit more complicated. I would not discuss it here. You can basically look at it up, but it would end up with mainly just two solutions. So either the normal acceleration is equal to the squared angular velocity multiplied by the radius, or is basically the squared linear velocity divided by the radius. So one of these two applies, and you can just basically remember this because and use it in the next problems that we will solve. As the way it derived, it's a bit more complicated than the tangential acceleration, and I don't want to cover it here, but you can look at it up if you want. Now regarding so let's take the first example to understand how we can do acceleration analysis of some algorithm or some actually mechanisms. So here we have the first mechanism. It is a planar mechanism. It is one degree of freedom we have here, and we have basically one link. For example, these are the links. So link, second link, which is this one, and the third link, and we have the frame. It has 1 degree of freedom. This is clear. We have a driver link, which is this one, and we have the dimension of this driver link, which is 250 millimeter, and we have the angular acceleration of that driver, which is basically 500 radian per squared second. And here we have the angular velocity, which is 225 radian per second. We have the initial orientation, which is 40 degree. Okay, so this basically, yeah, so the mechanism is basically used to push these boxes, for example. The input link, which is this one, is driven by electric motor, which has angular velocity and has acceleration. So usually the acceleration and velocity, mainly the angular and the angular velocity and acceleration of the driver link, because as I said, they are linked to the electric motor, which you control, which means that you actually your inputs are this velocity and acceleration. And knowing that the input link has a length of 200 millimeter, determine the acceleration of the endpoint of the input link in the position shown, which means that we want to actually get the acceleration of point A. Okay. Now, whenever we say we want to get the acceleration of point A, we look at point A, what kind of movement it has. It has actually rotational movement. Since we have rotational, that means we have two components. We have the tangential and we have the normal. If it has straight movement, like moving on slide or in prism, that means it has only tangential acceleration, okay? So here we have two components. That means this is what you see here, that we actually need to estimate the tangential acceleration vector and the normal acceleration vector. Now, we know that it's 40 degree, and we know that the normal acceleration lies along the radius of rotation. We know that the tangential acceleration is always perpendicular to the radius. That's why we know their orientation already. Because orientation is not an issue. What is the issue now is their magnitude. So of course, after we need then to get the total acceleration, which is basically a vector that represented by the sum of the normal acceleration plus the tangential acceleration. So this basically represents these two accelerations. And yeah, so the tangential and normal represent the projection of the total acceleration on these two axes. All right, so this basically we know that this is a 90 degree between normal and tangential. This is the total acceleration, which we need to get its beta here, which represents its orientation. Now, how we start? So we know the angular acceleration of this link, which means any point on that link has the same angular acceleration. And this is why we can apply directly this formula to get the magnitude, right? Because we know the angular acceleration and we know the radius of movement. So we can actually get this. And we can also get this because we know the angular velocity. So we can actually apply this one. If I don't know the angular velocity, but I know the linear velocity, then I can apply this. Anyway, if I know one of them, actually I can derive the other one, as you know. So this is what we have done here. We applied the first formula and we got the magnitude actually of the tangential acceleration, which is 125 meter per squared second. And so this is basically for the tangential acceleration, and we know already its orientation, as I said, from here actually, so which is a 50. Just here, important to see what this sign is representing. So this is the reference axis, which is actually our x-axis, which is all this one. And what we are seeing here, just to represent the sign of this orientation, that this is like 50 degrees in this direction. Okay, it could, for example, be represented like if, for example, it is more like this orientation, which is basically 180 plus 40 plus 50, then it's basically would be that rotation. So basically it's either 50 or 50 plus 180, but in this case you would have different orientation, or basically different sign. And so this basically, here we have 50 and represented with this sign you can consider, just to show you how it is derived. And this is represent the vector as a whole. So here we have the magnitude and the orientation, and now we have the vector as a whole. Now for the normal, as I said, we take the second formula, which is represent the normal distribution. We could get its again here it's a magnitude, and also we know its orientation, which is represented in this way. Okay, again like here. Now for the total acceleration, as I said, it's a sum of two vectors. So the first thing to do is here we can actually apply here some vectors laws basically, and we can say that if I'm summing two vectors, then basically the magnitude, or yeah, so it's not. So as I said, we have the total acceleration, which is if I project this total acceleration on the radius of movement and on the linear velocity axis, then I get two accelerations, and these accelerations are tangential and normal. So they represent the projection of that total acceleration on these two axes, which means the magnitude is basically the square root of the sum of squares here, and this basically gives me the magnitude of the total acceleration. And here I can get the orientation of this total acceleration by also the same, because they are the projection. And here we have the arctangent of the basically the tangential over the arctangent of the normal, and here we get the orientation bit of the total acceleration. Now what we are seeing here basically is that this is the enclosed orientation, and if I want to get the orientation of the total acceleration with respect to the reference axis, which is this one, which is our x-axis, we are just summing beta with 40, and then it will be this angle. Okay, so this is what we see here. So it will be 78, and it is that orientation. And here we have 200 meter per squared second as a magnitude. So next, as in velocity, we have relative acceleration, because we have some links that are driving other links. So there is relative motion between them that is represented by the velocity and acceleration. So with velocity, basically, the following notation is used to distinguish between absolute and relative acceleration. And this is the same here with acceleration. So we have the absolute acceleration, and we have, for example, the absolute acceleration of point A and B, and we have relative acceleration between them, which is basically the where B is moving with respect to A, right? So if I had, let's say, two links, and the first link, or the end of the first link, is a point A, and the end of the second link is point B, that means A is driven by the motor, let's say, which is at the frame, at the base, and A has absolute acceleration and velocity in this case, because it is the first moving, let's say, joint. Then we have B, which is basically moving with respect to A. So of course B has absolute acceleration, but it has relative acceleration, and its absolute acceleration actually is equal to the absolute acceleration of A plus the relative acceleration between them. Okay. Now this is the velocity, and there is a basic velocity, but it is the same story with the acceleration. So exactly the same. Now what we can do, of course, is when it comes to acceleration, as we have talked, acceleration actually is composed of two components, or of two vectors. So the acceleration of point B is equal to normal acceleration of point B plus the tangential. Same here, same for relative. Okay. So let's take an example of that. We have a mechanism, and this mechanism, as we see here, it has basically this kinematic vector, or sorry, diagram. It has one link, second link, and a third. So we have the frame, of course, 1, 2, 3, 4, and 4 is sliding. Okay. Now we have the driver is here. We know its angular velocity and angular acceleration. We know the initial orientation, which is 30 degree. Now the electric motor rotates counterclockwise, so it's rotating in this direction, and drives the free end of the motor, which is point B, at velocity of 12 inch per second. So this is basically the linear velocity of point B. So we know the linear velocity of point B in this case. Additionally, the crank is accelerating at a rate of 37 radian per squared second. So this is the acceleration. The top portion of the axle is moving toward the left with a velocity of 9.8 inch per second, and is accelerating at the rate of 82 inch per squared second. Now we want to determine the relative acceleration of point C, this one, with respect to point B, this one. So there is, of course, relative acceleration because point B is driving point C. Now, as I talked before, point C is moving along this line. So the first thing that we can just think of is that this point doesn't have normal acceleration. So, and we know that is moving in this direction along this line, or actually we know if we are moving in that direction, so if we are rotating counterclockwise, that means the movement is in this direction. So it has a tangential acceleration only, which is along the linear velocity, and it is in this direction. So we start with the first vector, which is representing the acceleration of point C. Now we know that point B is rotating. That means it has both components, which are the tangential and normal acceleration. We know that the normal acceleration is basically along the radius of rotation, and we know that the tangential is 90 degree or perpendicular to that line. So this way we can actually start, for example, with the first, and you know its direction, so you can just draw this but the other direction because you know that is the orientation, and then 90 degree this axis. And now it's clear here graphically that this has not closed, and it's not closed because what is missing, of course, is the angular acceleration between both. And this is the total sorry, not the angular, relative acceleration, and this is the total relative acceleration, which itself, right, is consists of normal relative acceleration and normal tangential acceleration. Now here what is basically we see, so we have normal, tangential, and this basically just representing what we have drawn here. So now we would start to get to our target. We look at what we have and what we can derive from what we have until we get to our goal. So the first thing we are doing here, we are determining the tangential acceleration of point B. So this is point B, and I want to get its tangential acceleration. I know its angular acceleration, and I know the radius of movement, so this is why I can estimate that easily, and I also know the orientation, so I know the tangential acceleration of point B. I can also get the normal acceleration of it because I know the linear acceleration, velocity of it, which is what's given. So I can apply that formula, and I know also because if I know this, of course I know this one because it's perpendicular to that. So the acceleration of C is given by, now the source of the point C is 82 inch per squared second, which is given. So this was the basically the velocity and the acceleration of 82. Now the relative acceleration in terms of points C and B, which actually what we want to get, is written as, so the relative acceleration is AC minus the AB, okay, because the point C actually is equal, or the acceleration of point C is equal to the acceleration of point A plus the relative acceleration between them, and here we are just reorganizing it. So the relative acceleration of point C with respect to B is equal to the absolute acceleration of C minus same this one, but now we put the two components there. So it's minus basically the first component, which is the normal, and minus the tangential. Now here it comes a bit more complicated. Now this is known, right? It's known, we know its orientation and we know its magnitude. This we know its orientation and we know its magnitude. This we know its orientation and we know its magnitude. So what we need now to do is basically to get this one, right? And the way we're getting this one is by doing some projection on the x-axis and the y-axis, or on the horizontal component and the vertical component. So because we have three vectors, and if I want to get basically a CP, I want first to project the three vectors on one orientation, which is basically on the horizontal component, and get the projection of the relative acceleration, and then I want to project it also on the vertical, and then basically I can get the, of course, the magnitude using that. So this is what we have done here. So this is the formula, and here we organize a table which is showing me all the vectors that I have, which is the absolute acceleration of C, the normal acceleration of P, tangential acceleration of P, their reference angle 180, 210, and 120, and their horizontal component. So we are just basically multiplying the magnitude with the cosine, the theta, which is the orientation basically, or the reference angle, and we are just multiplying the magnitude with the sine, and we are getting their projection. Okay, the horizontal component projection and vertical component projection. We are applying these two formulas, and we are getting basically the projection of the relative acceleration on the horizontal part and on the vertical part, and we can get the magnitude there, and also I can get the orientation there. Okay, so the relative acceleration then of C with respect to B is given by that, so by the magnitude and orientation. Now the last part here, because this is the total acceleration of the total relative acceleration of C, and we can also get the tangential relative acceleration and tangential and normal relative acceleration. So if I know basically how to project that, then I can have the magnitude with the sine 20 degree and the magnitude with the cosine 20 degree. And how we estimated that, this is the link, right? and the relative acceleration is basically the acceleration that is connecting point B and C. And the total acceleration that we have estimated actually is this one here. So what we have done is we project this one on first this on the radius of rotation, which give us the normal, and of course the other one which is perpendicular to that, which give us the tangential. Now this is why you have 20 degrees there. So this is how we got the tangential acceleration and the normal acceleration. Now here the interesting part. Why we did that? Because let's say I want to get the rotational acceleration of that link, which is the second link here. And I can get that now by dividing the tangential acceleration of that link, which represents the tangential relative acceleration over the radius, which is over Cp. And in this way I could get the rotational acceleration. Okay. So it's not that complicated. You just need to go through it slowly if you don't get it for first time, but it's not that complicated. Now this is your next homework. We have very simple here actually mechanism. It's only one link, but has 2 points, A and B. The link is rotating counterclockwise at a rate 200 radian per minute. So this is the angular velocity, and accelerating at 400 radian per square second. So this is the angular acceleration. We need to determine the total linear acceleration of point A and B. Okay. Well, we know basically the first orientation of A and the first orientation of B. So this is regarding this session. In the next session, we will talk about now spatial mechanisms, and we are getting closer to robotics manipulator. Thank you.